Hello, 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 hello. Hey, hey, everybody. How's everything going? I hope your day and or evening is going well. So, this is a live stream called Astronomy Daily Live, and I'm here every single day at 2 hours UTC, come rain or come shine. Uh, yeah, and we're going to spend the next little bit, maybe an hour, maybe more than an hour, just talking astronomy. Getting together with some friends around the world, and talking about a topic that we are passionate about and like to talk about as much as we possibly can. That's sort of my excuse, for coming here every single day. Uh, it's something that I just cannot get enough of and thoroughly enjoy, to think about and to talk about and to speculate on and all of that. And astronomy sort of offers the whole thing, right? It's sort of a study of everything from the extremely small, the subatomic, up up to the galactic, universal, all of that, and not only in space but in time and in um, color. Now, I'm gonna remove this kitty because she is being a major pest. So my apologies for having to exit so early, but now she has to go. She has to go. So I will be back in just one moment. All right. So this is Astronomy Daily Live. You can call me Cosmic, and I'm here every single day at 2 hours UTC to talk astronomy for a little while at least, maybe an hour, maybe less, maybe more, something like that. So hope everybody's doing well. So this is just a casual get together of friends. It's like um, I'm gathering together in a circle, but a casual one. Uh, and here we are, skeptical, but I'm open-minded about about all things, and I hope the quality is relatively high. Still, definitely on a learning curve in terms of that, but with some time and maybe a little bit of help from you folks, I can get better and better and better at these kinds of things. So whether you're new or you're an amateur or a pro, you are welcome to come in and let's talk about um, all topics, all topics related to astronomy. Let's get into it. Um, so uh, you know those kinds of things um, can be suggested by you. I'm more than open to talk about pretty much anything astronomical. Get my camera straight here. Drive me nuts. All right, there's absolutely no improvement there whatsoever. um, so whether you're new or a pro or some level of being an amateur, you are welcome in here. And as I said, I think the entire group should sort of lead the discussion and lead us down paths of discovery and learning, but also you know we can disagree about things. That's part of science, and that is one of the nice things about science is that we can disagree in sort of a civil way, and because we're just sort of trying to get to the bottom of things, trying to understand things a little better. So why not? So I'm going to get over here and look at my chat. Chat, 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 chat. Let's see. I'm running a little behind with all of these things. So if no topics in the group are coming to mind, I've got a whole bunch of them right here in my back pocket that I can easily pull out, and we can chat about those things as well. And one of the things that I like to do, and I'm probably going to get into that tonight, uh, is visiting archive.org. Uncle Bill is in the house. Well, thanks for coming in, Uncle Bill. Again, you're a great supporter, and years from now we'll look back and say, "Do you remember when? Do you remember when?" So yeah, I hope everything is going well over there. But yeah, archive.org is this really great site, and I've shown it um, quite a few times uh, on the live stream here, and I'm going to regularly be going back to it because it is updated every single weekday. Uh, they add between I don't know 8 and 20 new astronomical papers. Now these are professional ones, but I think that at least a lot of them um, uh, can be viewed, of course, and I think a lot of understanding can come um, from those things, even if you don't quite follow all of it. Some of these papers are pretty heavy in the math, so that's pretty hard stuff. But I always say start with the pictures and go from there because the pictures, and there's usually like a caption underneath on the pictures. So start there. See what you can get out of those. So what happens is professional astronomers they they're conducting some kind of research, and sort of the final uh, well, the end product of that research is usually a paper of some sort that is then submitted to a journal, and that paper is usually scrutinized by some peers, usually anonymous peers, not always. That and these peers are sort of knowledgeable in the subject matter of the paper itself, so they can give sort of useful critiques, um, and ultimately it's sort of those peers that recommend if these papers uh, are accepted for publication or not. By the way, the chemical of choice tonight is hydrogen hydroxide. Cheers. Ah, awesome. Very awesome. So it goes through peer review. That's what that's called, and there's a lot of controversy about peer review, sort of keeping um, uh, uh, maybe controversial topics out of the journals, maybe too theoretical, too woo woo, um, that kind of thing. So there's sort of a fine line there, because that's oftentimes a subjective call, and most astronomers are they it's well, there's a particular dogma that um, goes along with all all the sciences. A certain list of beliefs and a certain storylines, and if you're on the storyline, then you don't really have a lot of trouble. But if you're off of the storyline, um, you can run into a lot of resistance, and that's good. That's good. That's what science is. It's skeptical. It's skeptical of new ideas, um, but a lot of times, what I don't see is hey there, Susan. Hey, what I don't see is a lot of open mindedness. It's trying to fit um, you know your current idea into the current paradigm, and maybe it fits and maybe it doesn't, and sometimes your success is gauged by how well you can fit into the paradigm. And yeah, that's not necessarily a good thing, because that's sort of getting away from science and getting into um, dogmas and beliefs, instead of you know looking at the data, comparing it to models, and saying, okay, you know this is it. This is it. Kepler, when he was working on the motions of the planets, he had been you know part of the dogma, saying that look, the orbits have to be circles, and these are the parameters and all of that, and he had observations that didn't that just didn't match that model, and so he had to be a good scientist and say, look, if the data says this and my model says something different, then my model is wrong. So let's look at what's actually happening. Make sure that the measurements are good. Make sure that the data is good, because if you have bad data, you're going to get bad results. Garbage in, garbage out. That's how that goes. So you got to make sure that the data is uh, as awesome as you can possibly make it, and then you can at least sort of hope that your results are going to be about as awesome as they can be. So he that was really, really hard, and it is really, really hard, to um, go against sort of the standard, because in the true um, scientific sense, you are going to be uh, 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 criticized and ridiculed, maybe made fun of, and that's really, really hard. That's really, really hard, especially when you've put a lot of work into things, and yeah, it's just really, really hard. So I don't know what got me started on that now. Yeah, that's kind of the fun thing too about this live thing each day is that one can start to ramble and go off on a tangent, and who knows where it ends up. So let's just go over to, oh, I I was talking about submitting papers. So once the peers sort of approve it, then it goes back to the publisher, and the publisher has to make sure that the formatting is right, and they create a proof that then the author or authors have to check, make sure everything's spelled right, make sure that you know any kind of plots or images look right or sort of in the right place. All of that, it's just checking a proof. Um, and once that's done, the paper is approved for publication, and then it takes a certain amount of time to actually publish it in the journal that it was submitted to. But in the meantime, as soon as it's accepted for publication, uh, these papers become what are called preprints, and that is exactly what the name implies. It's the paper as it is, prior to publication. So let's go over to archive, and that's what archive.org is all about. I'm going to share my screen, and then we're going to come over here. And while we're doing that, I'm going to load up my smartphone like that so I can watch the video go. I'll hide that. Let's go over to archive.org. So it's ARXI, can't spell, XIV.org. So the X is like the Greek letter chi. So archive.org, not arxiv. And as you can see here, it's hosted by Cornell University, and it's not only astronomy and astrophysics, but it's all of physics. Okay, all the astrophysics, all the condensed matter, high energy, relativity, et cetera, et cetera. Then it gets into mathematics, computer science, biology, finance, stats, electrical engineering, and economics. So these are all of these are the latest scientific papers on these topics. So this is sort of like the bleeding edge of these things. So top of the list, naturally, is astrophysics. And what we can do here is we can look at the newest ones. These are the ones that probably, let's look here, probably came out today, which is the 20th of February, 2018, UT time, that is. This live stream starts at 2 hours UTC. So 2 hours UTC, right now it's 2:19 UTC on the 20th of February, 2018. And so these are the latest and greatest papers all about astronomy. So what I like to do is I just like to go through the titles. And if the title looks interesting, then I'll read the abstract. That's what these are. This is like a paragraph or so, a very, very condensed, brief description of what they're going to talk about in the paper. So let's see, cooling neutron star crust after recurrent outbursts. ALMA. ALMA is a radio telescope. Actually, I think it's a sub-millimeter, if I remember right, telescope down in Chile. It's a bunch of telescopes, uh, all sort of combined into one thing. Maybe someday we'll look at Alma in more detail. It's pretty awesome. It's doing some pretty amazing stuff. Influence galaxies from mass function, the vector photosphere of the red supergiant CE Tau. Okay. Interferometric imaging. Oh, VLTI. So that's probably radio observations. Reducing and analyzing the fat survey with the cloud. Evolution of H2O production in comet C2012 S1 ISON as inferred from forbidden oxygen and OH emission. Type 1A supernova light curves, plasma diagnostics. Some of these things I just don't have a clue. I don't have a clue what they're talking about. Let's see the structure dynamics of subparsec scale jet and M87. Whole space telescope observations of extended O3 5007 emission in nearby QSO2s. I don't know what a QSO2 is. Okay, it's a type 2 quasar. Well, I don't know what a type 2 quasar is either. These are, all these papers you can sort of use to educate yourself on stuff. If you find a term like that, like a type 2 quasar, it's like, what is a type 2 quasar? Well, you can look in the paper and they'll probably describe it a little bit. But you can also use the internet to dive around and see what you can find out. And maybe you got to start with what's a quasar, and then it's like, okay, there are different types. All right, well, what's type 1? I mean, if there's a type 2, that sort of implies that there's a type 1, right? So yeah, just lots of paths of investigation here for sure. Properties of decameter 3B-3 pairs, huh? I have no idea what those are. Mega metal poor dwarf star. Mega metal poor. Only a handful of stars have been identified with an iron abundance of less than -5, and only one at -7. These stars are very large carbon to iron ratios. Okay. So just not a lot of iron in those stars. Solar type 4 bursts at frequencies 10 to 30 megahertz. That's microwave. Results of first observations of type 4 bursts at frequencies of 10 to 30 megahertz are presented. These observations were carried out at radio telescopes during the period 2003-2006. So see, they collected this data like over a decade ago, and they're just writing a paper about it now. That's pretty amazing. Either this is like archive data, or I can't imagine that it took them that long to go through all the data. So it's probably archived. More kind of interesting. Zevatron, cosmic Zevatron. Okay, it's just I don't, after Terra, or Terra? No, it's not Terra. It's what's T? Oh wow, I don't know. That's a lot of energy, whatever it is. 1 tera electron volt. What's after Tera? It's a Z. I don't know what Z is, but wow, that's a lot. That's a big number. 10 to the 21st. Huh. K2 super stamp. Release of calibrated mosaics for the Kepler K2 mission. Ah, so here's just some calibration data from Kepler that they wanted to release into the universe. So SOHO and SDO are uh, satellite observatories that are looking at the sun. Primordial black holes and uncertainties on choice of window function. Okay. Surface person galaxies. Sensing twins. Stellar hierarchies that form sequentially. Long period massive binary. HD 54662 revisited. Huh. Let's just see what HD 54662 is. So all of these you can grab a PDF file of the paper itself. So this is from the horse's mouth, which is always awesome. Don't have to read a news article about it. You don't have to hear about it anywhere. You can dive right into it. Zoom in a little bit. You can go one more. Nope. Just one more. Yeah, we can do one more maybe. So there's the abstract again. Some journals are doing this now, where they have these various parameters. There's a context and the aims and the methods and the results and the conclusions. Huh. So there's a different there's a difference between results and conclusions. Yeah, interesting. So over recent years, the question of the incidence of binarity among population 1 O-type stars, and O-type star is a very, very massive, uh, hot star. It's an O star. Stars research claim that more than 70% of O stars are currently members of binary or more um, systems. High percentage of multiples include all kinds of systems, from very hard systems with short orbital periods of a few days up to weakly bound systems with orbital periods of decades or even centuries. So that's pretty cool. In between these two extremes lies a region of the parameter space that is currently the least known. In fact, very few O-type binaries are known to have orbital periods longer than a year, but shorter than a century. Oh. So an interesting target in this context is HD 54662. It's the brightest and earliest member of a of this association, which is just it's just a loose association of stars, not even really characterized as a cluster. It's just an association. It's a runaway star because it has apparently created a bow shock in the interstellar medium. Oh, that's kind of cool. The multiplicity of the star has been uncertain for many years, so they weren't quite sure if it was, like a binary or more star. But yeah, they looks like they've sort of confirmed it. Yeah, it was resolved in interferometry with VLTI. VLTI, um, I don't know what that one is, but I think that's radio radio as well. Proposed a full interferometric orbit of the system. They affirmed that the 558 days orbital period proposed is too short and rather favored a period of 2,103 days. So it sort of looks like maybe the period is still under some question, but it is definitely a binary for sure. Okay, peta, exa, iota, zeta. Okay, so zeta electron volts for that other thing. That's insane. Yeah, that's totally insane. Thanks, Uncle Bill. Um, two massive stars are bound by gravity. Their winds interact, and this interaction produces signatures over a broad range of wavelengths. So yeah, uh, these winds collide, and that makes for a lot of excitement. So yeah, so they're seeing X-rays all the way through radio waves. Pretty good. Good. Let's see. I have to zoom out a little bit here to see this table. Okay, so this looks like, yeah, so this is just a list of the observations that they made. This is sort of, the common theme in all of these papers is that, sort of the problem is presented, and then observations uh, are presented, and then they go through how they reduce and analyze the data from their observations, and then they go through the results, and they discuss their conclusions about what they found, if there were any problems, anything like that. So 15 spectra were obtained. So these are spectrums, looking at the spectra of these things. So the light coming in from this system is spread out into like a rainbow, and that rainbow, of course, can extend beyond the visible. It can extend into the infrared and into the microwave and into this submillimeter and into the radio, or it can go the other way too, and go from blue to ultraviolet, uh, beyond ultraviolet, yeah, X-rays, cosmic rays, gamma rays, that kind of stuff. So give me the whole thing. It sort of looks like in this case, um, it was part of the VLT, which I think is an optical telescope in don't remember exactly where that is. So lots of observations, lots of observations. RV1 and RV2. So that looks like radial velocities are determined from the spectra. So that's kind of cool. That's one of the pieces of information that you can obtain from a spectrum is you can measure uh, the relative velocity to us. Uh, and in this case, it's called um, radial velocity, which is just how far uh, either towards us or away from us it is moving. I don't quite know what RV1 and RV2 is. We'll have to look in the paper itself to see what that actually means. I'm sort of looking here. I don't see for all optical spectra we use the tune with an IRAF along with the list of telluric lines. Spectra were continuum normalized using uh, Midas routines and adopting the same set of continuum windows. The full list of our 39 optical spectra are given in table 1. Let's see if it talks about what RV1 and RV2 are. I'm not seeing it anywhere. Anyway, this just, oh, here we go. So analysis. First attempt to measure the RVs. So they're talking about the RVs there. So, part of reading papers is sort of going back and forth like this to sort of, see where they first reference various terms. It's the first time they talk about RVs. At least I'm not seeing a reference to RV in here anywhere. Yeah, cool. Yocto. 1/70th. Ridiculous. Just ridiculous names. Yocto. Yocto. Let's see. Well, I guess this is the first time they talk about the RVs is right here. The exterior observation of different epochs, we see a clear reversal in the asymmetry of the profile of the helium-1 at that wavelength, 5876, and helium-1 at 7065 lines. Behavior reflects the SB2 signature already pointed out. Okay, so the radial velocities of the components. That makes sense. So they can measure, how fast each of the components of this binary star system are moving relative to us. So that's what those numbers represent. 1 and 2 look like the components. Yeah. Let's see. Oh yeah, it's just a very, very detailed description of how they collected the data and then how they're analyzing at least this part of the data. So they're getting a period of 2104 plus or minus 13 days. See figure 2. Let's look at figure 2. Figure 2. Okay. Periodogram and spectral window of the primary radial velocities of HD 54662 over 1 over D. The inner panels zoom in on the region near the highest peak. Okay, kind of interesting. Yeah, don't quite know how to read that, but let's look at these guys over here. So orbital solutions. So they can make these observations and actually calculate an orbit. So they can see the period. Let's see. This is full set of primary radial velocities. Period in days. V naught. Don't remember what V naught stands for. Okay. Temperature? Is that temperature? No, that's time. That's the time of the observation. And a bunch of other parameters here. My cursor is really messing things up tonight. So then they have similar elements for sort of the combined primary and secondary. It's a little confusing. Here's some pictures. We always like pictures. Orbital solution. Top panel, the SB1 solution was computed from the full set of primary radial velocities from literature, assuming that there's an eccentricity of 0. Eccentricity of 0 means it's a perfect circle. So the mass ratio determine. Yeah, is it E of 0 is a perfect circle? Pretty sure. Okay, so this top panel is using sort of old data, previously published data, and I guess the bottom panel shows computed using only the new these solid, like the solid line and this dotted line is just a fit to this data, and this is doing exactly the same thing, but it's only fitting the new stuff. Although it looks like they're showing some of the old stuff. I mean, yeah, kind of hard to tell. Not really diving into the paper. So here are some spectra, just a little bit. So that's what at least a portion of the spectrum of this binary star looks like. And these are what are called absorption lines. See how they go? This, um, the y-axis here is like an intensity. So everything is normalized to 1, but then all these things are darker than that, right? Because they're less than 1. So that's called absorption. And along this axis is the wavelength in angstroms. So they're going from 4,000 angstroms to 4,300 in this first one, then 43 to 46, and 46 to 49. So they're looking, they're sort of looking in the that's pretty blue, right? It's going from like the indigo through the blue is what they're looking at here. Yeah, so those are just spectral lines, and each of these lines represent an element. You can sort of see this is called hydrogen beta, so that's identifying hydrogen. And here's a helium 1, so that's identifying helium. Here's a hydrogen delta, so that's identifying another um, absorption line of hydrogen. There's some helium lines in here. Look, there's some carbon 2. Let's really zoom in on this now. We can look at these spectra for a little while. So carbon 2, so that's ionized carbon. That means that I think the 2, pretty sure that the 2 means that it is missing 2 electrons. So normally carbon has 6 electrons. It's missing 2. I think it's missing 2. Could be the other way around. Maybe it has 2 extra. I'm going to have to check that. I think it's missing 2. So it, it's emitting, or it's absorbing a little bit of light there. But you can also see that they've identified magnesium 2. It's more helium, more hydrogen. Let's see what's over here. There's hydrogen beta again. I think this must just be a different data set or something. Let's find out. Okay, so this is the spectrum of the primary star, the main star, and this is the spectrum of the secondary star. So the secondary star is orbiting the primary star. And as you can see, if you compare these two things, for instance, here's sort of a double line here, and if you look in the same place here, there's not much of a double line at all. The depth of this one is much more than that one. Same goes for this line here. See all these complicated things here? Not very much there at all. So yeah, these are two different stars, and so they're going to have they're going to be made of slightly different things, either in terms of what they're actually made of, or just how much of a particular thing they have. Usually these depths, how dark these things go. Back up here. How dark these are is sort of an indication of how much stuff there is. So you can generally say that, okay, if this is deeper or darker, then there's probably more of this stuff in this star than there is the same stuff in that star. So I hope that makes sense. Just giving you a little show in terms of sort of picking out features inside of spectra without necessarily having to understand exactly what's going on here. But you can definitely tell that there are some differences and there are some similarities too, right? So H beta, hydrogen beta, is in both of these stars, and hydrogen uh, delta is in both of these stars. So we can definitely say that both of these stars have hydrogen in them. Both of these stars have magnesium. Both of them have helium. They've identified pretty much the same things in both. Some of these lines they haven't identified, which is a little strange, I suppose. Um, yeah. Hey, Uncle Bill, we get into uh, lots and lots of levels here. So OMC Triple X is saying something. Your latest episodes and company make this channel an unwelcoming environment to anyone who doesn't have a PhD. Yeah, okay. Well, uh, we're going to switch around a little bit. This is for everyone, and so yeah, I like to dive into things at various levels, and there are definitely shows that I've shouted out, to um, get into the basics if that's where you are. um, this particular live stream is going to try to cover uh, a, a much broader area. And so, I like to get into the basics for sure. I like to go mid-level, and sometimes I like to go heavy. So that's one of the cool things about a daily live stream, is that you don't have to show up here uh, all the time, and not every show is going to be for you. So yeah, I think that's one of the niches that I'm trying to fill, and yeah, I think that'll work out really well. So yeah, I totally agree that sometimes it's going to be heavy here, and I'm going to lose a few of you, but that's okay, because tomorrow or the next day, uh, you know we'll hit some lighter things, and yeah, I'm just trying to give a diverse thing. So yeah, um, don't feel as though you have to hang if things are getting too intense, or going so way over your head that it's just you know not working at all. Yeah, that's sort of the nature of the show. Oh, and PhDs are just letters, just letters. Don't let those letters intimidate you in any way, because anybody can understand um, this stuff if you really, really want to. Um, it's hard stuff, um, but that's what makes astronomy very, very cool. Is that it can be very complicated, very complicated. All right, well, let's keep looking at this binary star for a little while. Okay, so they're creating a model atmosphere and seeing what happens with that. Looking looking at measuring the temperatures. So very, very, very hot. 37,000 degrees Kelvin is very, very hot. Room temperature for us here, I think is around about 300 Kelvin. So this is 100, yeah, 100 times hotter than sort of room temperature. So these are really, really hot stars. As I said, the O stars are very, very big and very, very, very hot. OMC, triple X, peace, and yeah, check in from time to time. No worries, no worries. So those are hot stars for sure. High gravity too. This is called log G. So it's just a log based thing. But yeah, that's high gravity too, high mass for sure. And then they have X-ray spectra. It just goes on and on here. It's amazing. So that's all the data and the analysis of the data. Now they get into a discussion. So even more pictures. Yeah, this is getting pretty heavy for sure. Without really diving into the paper, I'm going to get lost really, really quick. But I think that's sort of a good level, to come in on from time to time to, you know, push yourself a little bit and see what's available. A bit more of that, another plot. So here they're talking about the bow shock. That's pretty cool. Oh, there it is. So there's this apparent bow shock. It looks like, just looking at the picture here, looks like the motion of this binary star is that way, and that coincides with this bow shock. That's kind of cool. So, this binary star is moving through sort of some thick stuff out there, and is moving fast enough to actually create like an acoustic shock wave, and there's enough energy in that shock wave to make it glow. So that's pretty cool. Yeah, I like I like variety too. So yeah, and that's sort of how I um, see this, and not every single show, not every single live stream um, is going to be for everybody. That's not sort of the nature of this show. I'm going to go all over the place. Sure. But I think what I'm going to do is exit this and come back to this mug. Oh, where is it? This mug, this one right here. And I got up really early this morning. I woke up and the brain just would not shut off at all. So it's like, okay, I'm gonna get up, but that was many hours ago, and man, I am toast. I'm toast. So I think I'm gonna cut this short for tonight. So I'm glad everybody was able to come in. If you're watching this in the future, um, make sure to subscribe. I think you can set the notifications so you can be told when I go live. And uh, but I do go live every single day at 2 hours UTC. So you'll have to figure out um, what that is for your particular location. Shouldn't be a big problem. Um, if you like this kind of content, hit the like. If you don't like this kind of content, hit the dislike. I appreciate any kind of reaction at all, especially early on like this. Yeah, I'm just sort of looking for um, reactions at this point, and whether they are positive or negative, I don't really mind. I'm looking for the absolute value. So yeah, absolutely. And make sure to share this video too. Spread the word. Let people know that I'm here at same time, same place, and I'm talking astronomy at many levels, many levels. Sometimes we can get a little bit heavy. Sometimes we can go a little bit light. Sometimes we'll go right in the middle. This is, it's not going to please everybody, um, but that's not why I'm doing this. I'm doing this because I like to talk about astronomy, and sharing the passion a little bit and getting together, with people who share a similar passion at whatever level, at whatever level. So yeah, I think I'm going to exit for now. It's been a good time, interesting paper. Um, I like to pull out these random ones and um, go through them with you live. I haven't I haven't looked at that paper at all. So a lot of it was and is way pretty much way over my head. But yeah, it's that level of understanding I'm still aiming for, and yeah, aim high, aim high for sure. All right, I'm gonna get out of here. I gotta get back up to the ship, and yeah, all right. So have a great evening and a great day. And yeah, I will see you again tomorrow, uh, 23 hours from now, 23 hours and 2 minutes from now. All right. Take care. Cheers and peace.